Hello, this is Miss Moore, and today during chemistry we're going to discuss molarity and dilutions. Today's essential question: how is molarity calculated? By the way, you're definitely going to want your calculator for this one. Okay, we're going to start with a few definitions about solutions because when you're calculating molarity and dilutions, you're talking about solutions. So, when we're talking about a solution, what that really means, it's a liquid mixture. And a solution is made of two different things: a solvent and a solute. And a solvent is the primary component, and it's a liquid. And the solute is the thing that's being dissolved in the solvent. And a solute can be a solid, a liquid, or a gas. Okay, let me give you a real quick example of a solution just so you have a visual picture here. So remember, a solution is a liquid mixture. So how about Kool-Aid? All right, so remember, a solution is made up of both a solvent and a solute. So what is our solvent? The solvent is the primary component, the liquid. And if I was making Kool-Aid, the liquid would be water. And then our solute is the thing being dissolved in water. And making Kool-Aid, we probably have two solutes. We have the Kool-Aid powder stuff, and we have sugar. So when I take my two solutes, the Kool-Aid powder and the sugar, I dump it into water, my solvent, mix them up, I get a liquid mixture known as a solution. All right, so now that we know what a solution is, let's talk about concentration. So the concentration of a solution is a measure of the amount of solute that is dissolved in a given quantity of solvent. So when we're talking about Kool-Aid, our Kool-Aid example, concentration would be maybe the amount of Kool-Aid powder or the amount of sugar per amount of water. A dilute solution, so a dilute solution is one that contains a low concentration of solute. So maybe we only used a little bit of sugar and powder. Okay, Kool-Aid powder. So that would be a dilute solution. Whereas a concentrated solution contains a high concentration of solute. So we used lots of sugar and Kool-Aid powder per the same amount of liquid. Okay, so now we know what concentration is. We know what a solution is. So on to what we really care about, molarity. So molarity is just one way, one unit, I guess you could say. It's one way to express concentration quantitatively, meaning with numbers. So instead of saying I have a dilute or a concentrated solution, I can give an exact number. So specifically, the definition of molarity is the number of moles of solute dissolved per liter, that's going to be really important later, per liter of solution. So basically, molarity is how much stuff in moles is dissolved in the liquid. Okay. So to determine molarity, we're going to use the equation. Whoa, one more step, there we go. Molarity, which is represented by a capital M, is moles of solute divided by liters of solution. And the units for molarity is mole per liter, kind of just like the equation. So when you give your answer, you can write capital M for molarity or you can use mole per liter. But when you're solving problems, it's really important that you use moles per liter so you can cross out units, because of course you're always going to write units and cross them out. All right, well, let's try a practice problem. We'll try two. So first one, a chemist wants to make a 7.5 liter of a 6 molar solution of sodium hydroxide. How many moles of NaOH will the chemist need to make this solution? I'm a big fan of lists to keep me from being lost, so I know I need molarity, moles, and volume in liters. So our molarity is a 6 molar solution, and we're going to be solving a problem, so I'm going to write that as 6 mole over liter. We don't know how many moles, and we do know that we have 7.50 liters. So now we're just going to take this stuff and plug it into the formula. Molarity equals moles over liters. All right, so we have 6 mole over liters equals X over 7.50 liters. All right, so from here we cross multiply, giving us 45 mole liters equals, crossing this way, X liters. Now, obviously you can kind of see the answer, but let's do things correctly. We'll divide both sides by liters, giving us 45 moles of NaOH. Now, our very favorite thing, we got to go back to sig figs. So we have 1 sig fig there and 3 there. So our final answer needs to have only 1 sig fig, right? So we have 45 moles. We're going to keep the 4 and drop the 5. And 5 is 5 or greater. So that brings our 4 up to a 5. And then whenever we're dropping a digit before a decimal, we need to put a placeholder. So we'll say our final answer is 50 moles of sodium hydroxide. All right, let's try another one. So what is the molarity of a solution prepared by dissolving 37.94 grams of potassium hydroxide in some water and then diluting the solution to a volume of 5 liters? Yeah, I don't want to have 1 sig fig this time. Let's make this 5. Let's make this 5.0 liters. Okay, so let's make our list. We have molarity, mole, and liters. Molarity is our X, right? What is? It doesn't give us any moles. Let's skip that for a minute. And our volume is 5.0 liters. All right, so what do we do about our moles here? Well, we're going to have to convert. They did give us grams, right? So we can convert from grams to moles. So we have 37.94 grams of potassium hydroxide. We want to know how many moles that is. So we're going to use 1 mole of KOH equals the molar mass of KOH, which we get by looking up the masses on the periodic table. So let's do that real quick. All right, so potassium has a molar mass of 39.10 grams, oxygen 16.00 grams, and hydrogen 1.008 grams. We add those all together, giving us 56.108 grams. We look at sig figs. Remember, we're adding, so we look at number of digits after the decimal. Least number is 2, so 56.11 grams. So 56.11 grams KOH on the bottom. 1 mole of KOH on the top. These cross out. So now we will multiply and divide, and I really hope I don't make a mistake here. I got 0.67617 1, etc. moles And we need 4 sig figs. So 0.6762 moles. So we'll put that in our list, 0.6712. I got a mess here. Let me clean this stuff up. That's better. Moles. All right, now plug and chug. We have molarity equals mole over liter. So that means we have molarity equals 0.6712 mole over 5.0 liters. So let's calculate that. All right. Hopefully a few of you were screaming at the screen saying, Miss Moore, stop. Let's fix my mistakes before we calculate that. Our moles is 0.6762. All right. Sorry about that. All right, let's put this in again. 0.6762 mole over 5 liters. And that gives us 0.13524 mole over liter, and sig figs 4 and 2. So we're going to keep those, giving us a final answer of 0.14 mole per liter, or 0.14 molar. Okay, so there's that for molarity. We now need to talk about dilutions. So what we're really talking about is we're going to prepare a solution. So often concentrated solutions are made. These are called stock solutions. So what you do is you make a little bit of a really concentrated or strong solution. And then what you can do is you can dilute it to whatever concentration you want when you need it. And diluting a solution will reduce the number of moles of solute per amount of solution. Because what you're doing is you're taking a little bit of very concentrated solution and adding water or some other solvent to it, which will increase the volume, keeping the same number of moles of solute. So you basically end up for less moles per amount of solution. Okay, so when you're doing dilutions, you're going to use this formula, M1V1 equals M2V2. This is super handy. Okay, and this stands for M1 and M2 are the initial stock concentrations of M1, molarity, and V1, volume. You note here I say volume, not liters, so you don't need to use liters in this case. And then M2 and V2 are the final molarity and volume. That's really all there is to it. We do need to try a quick practice problem though. All right, let's try one quick practice problem. So how many milliliters of a stock solution of 2 molar MgSO4 would you need to prepare 100 milliliters of 0.4 molar MgSO4? So we need to figure out what goes together. So we know that we want to know X, right, is our how many milliliters. That's going to be our X of a stock solution that is 2.00 molar. Those go together. And what we want to be making is 100 milliliters of 0.4 molar MgSO4. It doesn't really matter which ones you label as 1 or 2, but I'll call this, let's see, this is our V1 and this is our M, that didn't work very well. This is our M1, and we'll call this one M2 and V2. So all we need to do is plug it into the formula M1V1 equals M2V2. So we're going to have our 2.00 molar. X, we don't know how much. And then our 0.400 molar times 100 milliliters. Easy enough? All right, so if we do a little bit of math here, we're going to end up, well, on this side, we'll still have 2.00 molar X equals 0.4 times 100. That's going to give us 0. No, try that again. That's going to give us 40. We'll deal with our sig figs later. That's going to give us 40 molar milliliter. Then, to get the X by itself, divide both sides by 2 molar, giving us 20 milliliters. So what you're going to have to do is what you'll be doing is you'll take 20 milliliters of our stock solution and put it into a graduated cylinder, and then, but you want a total of 100 milliliters of solution, right? So then you add 20 milliliters of our stock solution, and the rest would be water, in this case 80 milliliters. All right, so our last step is we do need to look at sig figs. So let's see. This guy here has 3 sig figs. This one has 4 sig figs, and this one has 3. So our final answer needs to have 3 sig figs. So we'll write that as 20.0 milliliter, which changes our number of sig figs without actually changing the quantity. All right, that's it for today. Have a good one.